some some number that you know that it doesn't go below? Like you need some.
Well, we do have that here.
Yeah.
I said that because 0.
Right. Okay. Right.
0 is the door.
Okay.
There's 0. I can't get beyond the door, and I'm always moving to the right. So something's got to stop. Okay. So again, these are numbers. The first number is the second, third, and gets 1, 2, 1 chopping, 2, so on and so forth. 2 choppings, 2 parts, 4 parts, 8 parts, blah, blah, blah. These are numbers, again, moving to the right. They're stopped by 0. They're now representing areas, not lengths. Doesn't matter. They're still numbers. They're moving to the right. They're getting closer and closer to something. Something's going to stop. So, but now we know exactly what that is. We don't even have to think anymore because this is not changed. This is R. And this is, we assume, the first intuitive leap of faith was that this is getting closer and closer to the circumference. So this is getting, let me draw an arrow, means getting closer, too close for comfort. Closer and closer and closer to 1/2 R times the C. But C now, we have a formula here. C over D is pi. C is equal to pi times the diameter. But the diameter is twice the radius. So C is equal to 2 pi R. So C is equal to 2 pi R. So this is 1/2 R times 2 pi what? R. 1/2 times 2 is 1. So this is pi R squared. Now, why is this example important? Because it links the problem of area with the problem of numbers. Now today, if you're a sophomore, a junior, or a senior in university, you take a course called Real Analysis. Well, it depends on whom you take it from. If you take it from me, I construct the real numbers from scratch. If you take it from somebody else that doesn't want to be bothered with that or doesn't see the point of that, you get an axiom system. And the axiom system for the real numbers says exactly what the Greeks should have realized. And we see it here. It's completely motivated by the problem of area. If you have a sequence of numbers, 1 number, 2 numbers, 3 numbers, going on, moving only in one direction, either to the right or to the left, but for which there's a wall blocking them, then those numbers are getting, there is a number such that those numbers are getting what? Closer and closer to it. It's called the axiom of completeness of the real numbers, and the intuitive meaning is the non-hole axiom of the real numbers. The real numbers have no holes. Now you can state that as an axiom, or you can actually prove it and by construction, but that's very complicated. Okay, now, so we've derived the area of the circle. The Greeks knew this. Now, the way I've treated this, you can immediately see the connection with the problem of what a number is, and the holes in the number system, or the potential manholes in the number system, with the problem of area. It's obvious. Problems of areas are complex figures. And tomorrow, or the next day, we're going to derive the volume of a sphere, as Archimedes would have done. You're going to see. And the surface areas. So it no longer becomes a mystery. Unfortunately, perhaps for the whole history of science, I don't think the Greeks used this derivation. Because had they used this derivation, they would have, they may have seen the connection, or they may have seen how to define number in a way that could have gotten them through the barrier or the problem of the existence of the square root of 2. Unfortunately, they were bogged down in all kinds of philosophical beliefs. Now, we know that the Greeks had a system of calculating areas. Now, some people believe that the Greeks invented calculus. For example, they could calculate the areas. And in fact, Archimedes and others calculated areas, and as we know, he calculated volumes, and he calculated areas of incredible regions. For example, Archimedes, one of his great fames was he calculation of the area of a parabolic segment. Remember, we know about parabolas from what? From Apollonius, from Platonus. Apollonius gave us the conic sections as actually sections of a cone. He named them. But one of the problems was, let's suppose you have a parabola, and you take any line intersecting the parabola like this. What is the area of this parabolic segment? Archimedes solved that problem. Among many other problems, like, as I told you, the area of the sphere divided the sphere, which was on his tombstone. In solving all these problems, he avoided completely the definition of what area was. He assumed that area existed. And the method he used was a method that went back to an earlier Greek. It was called the principle. I have 5 minutes, but the lunch lady's coming. I'm just going to complete the logic. The principle of exhaustion. And it's you exhaust
like our teaching, right?
Right. Principle of how to exhaust ourselves, right? Here's what Archimedes did.
It goes back to Eudoxus, by the way, who I talked about
Principle,
yesterday.
Eudoxus invented it. And Eudoxus invented it, didn't I say that? And Archimedes perfected it. Now, and somehow this method, unlike my method, hid the connection between the holes in the real number system and the problem of area. Why did it hide it? What did Archimedes and Eudoxus do? Well, what they did was they took inscribed. They took, let me go back to big L here. Go back to big L, and now call that little l, for 1, and call that little l 2. Okay? Now, here's what they did. They took the areas of the inscribed triangles. You added them up. They took the areas of the circumscribed triangles.